Hi all, welcome back to Microbiology Lectures. We're going to continue talking about ways at which we go about controlling microbial growth. Today we're going to talk a little bit about numbers of microbes and how that goes into the methods at which we control, or maybe potentially the new methods that we design. Okay, so we know that if large populations is pretty basic knowledge. If you have a really big population of microbes, it's harder to destroy, or it takes longer to destroy that population than a smaller one. And so often that kind of gets into the growth phases of microbes. So clearly, if we can figure out a microbe during the lag phase, then it's a lot easier to knock that population down to zero than if it's late in the exponential phase or even into the stationary phase before you identify what microbe it is. So time is important when it comes to treating or dealing with populations of microbes. Okay. Apart from that, it's also how we deal with the microbe initially. And so what we've found out for many processes, whether we're sterilizing or disinfecting, a huge benefit to that process, that sterilization or disinfection process, is to wash first. And that washing of that material first, not only does it allow us to get colonies or populations in kind of this region, the lag exponential region, it also allows us to remove biofilms. And so if they're later in and they're starting to build biofilms, or they're starting to build secondary metabolites, scrubbing helps remove those biofilms, helps open up the population to whatever method we're going to use for sterilization or disinfection. Okay? Along the same lines is how we determine, one way in which we determine whether or not a chemical is a good disinfectant, or does a chemical have the capability of being, having sterilized properties, is to look at the decimal reduction time, or the D value. And the way the D value works is we're often interested in the ability, or how quickly we can take a population. Like here, let's say we have 10,000 different microbes, and drop it by 90%, so we only have 1,000 left. That's the D value, or the time it takes us to do that. Okay? Obviously, the quicker we can do that, the better. And so what we don't want to see is, something like this, where we have a microbe that's going through the lag phase, exponential phase. We treat it, and then after the treatment, we get a death phase, or a declining phase. But it's not enough. It's not that 90%. And then you get a bunch of bouncing around. They prolong, they stay for a long period of time. If conditions get better, they could shoot back up into exponential phase. But that's not what we want to see. We want to see a reduction time, a D value that's going to reduce it, by 90%. And so we'll come back and talk a little bit about this, but often we can compare different things. So maybe we're comparing different temperatures in, say, like an autoclave. And so maybe we're comparing, how does 110 degrees Celsius work versus 115 versus 120 versus 125. And so we might have a D value for each one of those temperatures, and we can see, like, well, how much time did it take for us to get that D value, that 90% reduction. I mean, we can do this based on different chemicals too, and so it's just a way at which we can put an actual value on the ability to destroy a microorganism population, or at least reduce it to a manageable number typically. Okay. There's quite a few things that can affect that D value though. Temperature, like I said, like sometimes we know the temperature is going to affect it, and sometimes we're interested in different temperatures. Sometimes it's related to pH, and then things that can get in the way is like, what kind of substance are you trying to disinfect or sterilize? Are there other species? Are these organisms forming biofilms with multiple species? These kind of things can get in the way and affect the D value in a negative way, I guess, or prolong the D value. So if there's multiple species, then it could prolong your D value. It takes you more time to get the same result, that 90% population decline. Okay. All right, so environmental conditions also play a huge role when we're talking about going through the process of sterilizing, disinfecting, sanitizing, these different things. What is present can have a direct effect on that. So, like, if we don't do a pre-wash and remove dirt, grease, bodily fluids, etc., it can interfere with heat penetration. And we've seen this from studies that have looked at surgical instruments that have been autoclaved and went through the sterilization process and then came out and they were dirty still. And 34% of the time when that was the case, okay, it was because there was there was little to no, or at least inadequate, cleaning prior to the sterilization. So things like dirt, grease, bodily fluids were not removed, or not removed in a systematic way, and so therefore it didn't matter that you stuck it in an autoclave at 121 degrees and for 15 minutes or 20 minutes or whatever. It didn't work. Like, it didn't clean it. Okay? And part of the problem is, like, all right, I mean, let's just go out there and say there's very few people that like to wash dishes. Like, it is not the greatest position, but it is extremely important from like a medical facility that we don't think of the individuals who are cleaning these medical instruments as glorified dishwashers. And that's a hard kind of thing idea to kind of get rid of, because their job is to clean medical instruments, and but it's so important to get for that initial cleaning, for the sterilization or disinfectant to work. Okay. The other thing that we know is that temperature and pH can obviously affect the or influence the effectiveness of different chemicals, and the ability to get a consistent D value is directly related to the temperature and pH. For example, we know that Microbacterium tuberculosis is killed by household bleach, but depending on the temperature will determine the time, or the D value, that is needed to kill 90% of the population. So at 55 degrees Celsius, it kills, or the D time is half of what it would be at 50 degrees Celsius. And so you add, the effect of potentially pH in there, and you have a whole bunch of things that can determine the rate or the D value that you're going to get from these different solutions. Risk for infection. Okay, this really is based on quite a few things, but often we're interested in, what's the medical instrument that is being used? And different medical instruments have different ratings on their risk for transmitting infectious diseases or infectious agents or pathogens. Obviously, ones that are in contact with body tissue are normally considered critical items, and so things, scalpels and forceps and things that actually come in contact with body tissue, they're called critical items, and they have a higher risk of transmitting infection agents, so therefore they need to be sterile, and so they need to have that sterile category. That sterile category, normally we say something is sterile if there's less than 1 in a million chance that there's a microbe on it. So if you were to take, say, a scalpel and you swabbed that scalpel and tried to grow on a media plate whatever was on that scalpel, you could grow 1 million plates and not have a single account of something being on that scalpel. That would be labeled as sterile. So basically meaning there's nothing on it, no biological or pathogenic material on that instrument. Okay? So lots of instruments fall in this category, most of which we can sterilize by using something like an autoclave. So most of these are metal instruments that can be autoclaved, or they're disposable instruments that, when they're being made, they're as sterile as possible. Well, they're sterile because they have to be. Okay. Another group would be semi-critical instruments. Okay, these are instruments that are often encountering mucus layers, but not penetrating tissue. So things like an endotracheal tube, or things that might be stuck into different orifices of the body for limited time or potentially a long time. Those are considered semi-critical instruments. Often these are rubber or plastic instruments, and so sterilizing them is very difficult. So sometimes disinfecting them is enough, so they must contain less than 100 microbes. And so sometimes disinfectant is enough. Other times the material, because of the material being used, you're not able to sterilize it using the methods that we talked about, like using an autoclave, because the temperatures are too hot and it will melt the material. So instead, these are considered disposable parts, and so they're prepackaged, sterile packaged, and they're disposed of after a single use. And then there's the non-critical instruments. These are ones that often are not contacting broken skin, or they're not contacting open wounds, maybe just sweat, these kind of things, and so they have less risk of a transmission, and they can be, it depends on the medical facility on how often these are cleaned. Some facilities are really good about cleaning blood pressure cuffs and stethoscopes and their countertops, and they have set procedures where after every use these things are cleaned. Others not so much. So again, a lot of the things that are non-critical instruments, because they're not contacting mucous membranes or body tissue, open body tissue, then there's just less risk for transmission, so there's less reason to be concerned with the potential of microbes. And so there's no minimum microbe number for these kind of pieces of equipment, but again, like, still probably should be sanitized if at all possible. Again, back to composition of the item. We've talked about this quite a few times. There are lots of items that are used in medical facilities, food processing facilities, etc., that are made of plastics or made of something that is heat sensitive, and therefore you cannot autoclave or sterilize those things using high heat. There are other things that other plastics or materials that even using radiation can't be done. So like using gamma rays or UV radiation might tend to break down that material or damage that material, and so even that can't be used. Often, the composition of the item is really important to know what the item is made out of, and whether or not you can stick them in an autoclave or stick them under UV lights or gamma irradiation. Okay. Some things that we often see or have had issues with kind of an autoclave situation are really sharp instruments. I mean, very, very fine blades. They have issues with being autoclaved. Yes, normally they're made out of metal, but like keratomes and things like that, often because of how sharp the material is and the edge, how fine the edge is, if autoclaved, due to the moisture, the steam, and the heat, they'll rust. And so many of these instruments are disinfected chemically instead of autoclave. Fiber optic devices, a lot of times they'll have kind of a rubber or plastic sleeve. Okay, same thing with implanted devices. A lot of these things, they have to be chemically disinfected. And there are some chemicals that we use that are sterilants. So keep in mind, it's not just high heat, high pressure, that kind of thing that can sterilize. There are chemicals that can and do sterilize. It just happens to be that it's more eco-friendly, probably, environmental friendly to sterilize using high heat and steam and pressure than it is to spray certain types of chemicals on the material. Although we'll come back and discuss that. Okay. So next time when we come back, we'll talk about some specific examples of how we go about sterilizing or disinfecting different equipment in different industries. Okay. So next time.